Hello, students. We're going to tackle 13.3, and this one does include the Pythagorean theorem, the distance formula, which is basically the Pythagorean theorem, and the equation of a circle, which you're not going to believe is the Pythagorean theorem once again. So all three of these tie in to be extremely closely related. And let's take a look. You've probably seen the Pythagorean theorem at some point in time before, but our goal here is to try to understand it and to be able to show why it is true. So the Pythagorean theorem talks about right triangle, and the right triangle has legs of A and B and a hypotenuse of C. That's the longest side in the right triangle. And so the theorem states that if you do have a right triangle with legs of A and B and a hypotenuse of length C, then C squared equals A squared plus B squared. They've written it in a strange way. Most of you probably remember it as A squared plus B squared equals C squared. Okay, let's take a look. Now, if you want to show why this is true, we would prove it. And there's many, many, many proofs that are available. There's actually a book by Alicia Loomis that had hundreds of different proofs. And I mean, fantastic book in my mind. For some of you, you're like, wait, every proof was the Pythagorean theorem. Yes. And they were all different. Yes. So here's a couple of approaches. Now, we actually saw how to prove this in the last chapter when we did similar triangles. Some of you liked that, some of you didn't. But the point of it was that you can prove this. We should not take mathematical statements like this as they're always true. What we should do is try to break it down. So I want you to take this right triangle that they have here, and I want you to notice one approach is to clone the triangle 4 times. Do you see them here? A and B right there. So there's 2 triangles and there's 2 more triangles. And then you draw the squares that are matched up and this is where you got to be kind of paying attention here, to make a very big square here, right? That's a big square. Okay. Well, the big square is A plus B on a side, and that area would be A plus B times A plus B. But that's also equal to all of the little shapes inside. And there's a square here that would be an A squared. We have let's see here, what do we have here? A B squared, right? And then on these, this is B times A divided by 2. So plus 1/2 B times A. So that's like one of these little triangles, but there's 4 of them. Okay, so there's 4 of those little triangles. Okay, so we can see that. That's the relationship there. Now look right next to it. What's right next to it? Well, this is what someone did. They took those 4 triangles that we had at the beginning, and all they did is move them around. So one triangle they put here with the right angle in the corner. They put another one here, again, right angle in the corner. Okay, right angle here, right angle here. So they moved 4 of them around. Okay. Now their goal was to say, hey, these actually have exactly the same shape. Why? The outside shape here is A plus B quantity squared. So that's the same. And if you notice, there are 4 triangles here. Okay, and that's equal to 4 of these triangles, which are 1/2 B times A. And then there's this other shape in the middle. Now that shape in the middle does look like a square, but we got to be certain that it actually is a square. And here's how we're going to have to do that. We have to justify it. We can't just say it's a square because it looks like a square. What we're going to do is we're going to number our angles. 1, 2, and then angle 3 will be what's inside. Now my hope is that angle 3 is a 90-degree angle. If it's 90 degrees, it would be 90 degrees around each of them. But let's see here, 1 plus 2. So let's see here, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees. Okay, and that's because they're supplementary. And now let's look inside one of the triangles here. what you notice is I have an angle 1 and I have an angle 2 and I have a 90 degree. So now I know the measure of angle 1 plus the measure of angle 2 plus 90 degrees is equal to 180. Well, take a look at these two equations. The measure of angle 1 is the same. The measure of angle 2 is the same. The 180 is the same. So that means that the measure of angle 3 has to be 90 degrees. And that is a huge piece for us, a big win, because it means the shape inside is indeed a square. And since we have legs of A and B, this would be C. So the square inside would be C squared. Why is this so cool? Now they look at these two sides because they're both equal to A plus B squared. And you could say, well, wait a minute, each of them has a component that is identical. If you remove those, what you have left is that A squared plus B squared on one side has to equal C squared on the other side, and you have just shown that the Pythagorean theorem is true. That is pretty cool. So you get to prove it. And in case you're wondering, yes, on the next exam, there will be one entire page that simply says, prove the Pythagorean theorem. I do not care how you do it. You got a lot of options. Okay. Let's see here. When they do the Pythagorean theorem, you'll see some applied problems. The applied problems will often give you two components, leaving one of them out. But if you set up the Pythagorean theorem, you will be able to find and solve using what we did in chapter 8 for the value of the missing piece. So this is 49, this is 25, this is x squared. Subtract, x squared is equal to 24. So x is equal to plus or minus the square root of 24. But remember, we're talking about shapes. It can't be negative. So x is the square root of 24. And that's how you can find those pieces. You can use your calculator to approximate with a decimal, but it's also good to know how to find the exact value. Okay. Now, this is basically the example that they used in the class, which is fine. There's nothing wrong with that. This is for a grade 8 classroom. And let's see here. Once again, here's a rectangular screen. What's the length of the diagonal? Now, if you're wondering where do we use this, this is actually how they measure the size of your television screen. It is not about your height and your width. It is about the length of the diagonal. So when you see a 70-inch screen, it doesn't mean 70 inches up or down or left or right. It's the diagonal is 70 inches. And that could mean something very different from one screen to another. Yes, they do not have to have the same size to have the same diagonal. We saw that with rectangles. The diagonal of a rectangle can be the same, and you can produce very, very different shapes. Let's see here. Once again, it says how far are the stakes from each other. So setting up a Pythagorean theorem, finding one of the links, it's a similar triangle, or in this case, congruent, you can find the other one. So it's all about applications here. Let's see here. How tall? Ooh, this is a three-dimensional shape. And in order to find a three-dimensional shape, you need to do the Pythagorean theorem twice. And the reason for that is, actually, you may not need to if they give you this slant height. They give you this slant height, and they don't tell you this FD, but guess what? It's exactly half of the length on the side. And so you will know these two pieces. The question is, what is the height? So you only have to use it once in this case. Sometimes we have to use it twice, but I'll save that for a little bit. All right, let's talk about some special right triangles. Special right triangles have unique properties. 45, 45, 90 triangle just means it's a 90 degree, and the other two are split equally, which makes an isosceles right triangle, and the angles being 45. So if we created sides and we just called them 1, then we would end up with 1 squared plus 1 squared equals c squared. That's the Pythagorean theorem. And 1 plus 1 gives me 2. So c squared is 2. So c is equal to the square root of 2. Again, it would be plus or minus, but we know we're dealing with side lengths. So for a 45, 45, 90 triangle, the ratio of sides is 1 to 1 to the square root of 2 every time. This is a huge savings. You may not have to do the Pythagorean theorem if you know your triangle is 45, 45, 90. That's because that ratio. So you can just scale that ratio up. The other one is a 30, 60, 90 triangle. And you can build this one yourself using a nice an equilateral triangle. So here they're going to use side lengths of 2. And the reason for that is you're going to cut this in half so you have a side length of 1. And then to find the missing piece, which we could call h. So we have 1 squared plus h squared equals 2 squared. That's a Pythagorean theorem. Bring the 1 to the other side. 2 squared is 4. Take away 1 gives you 3. So h is equal to the square root of 3. So that means the side lengths are 1 to the square root of 3 to 2. So the long side or the hypotenuse is 2, the short side is a 1, and the middle side is a square root of 3. And don't forget, this right here, this 1 to 3 to root 2, or 1 to root 3 to 2, sorry about that, they all go in order of the angles. So the 30-degree angle is opposite the smallest side. The 60-degree angle is the next, and 90 degrees is the top end. For those of you who did take a little trigonometry, if you did some trigonometry, the only difference between what we're doing in trigonometry, if we had a 30-degree angle, is in this, we would say something like, let's create specific ratios, and we know these lengths. So we would create ratios like the opposite over the hypotenuse, opposite over hypotenuse, and we create that ratio, and we see it so often, we give it a name, and the name of that ratio is sine. Now, we don't write it that way. We typically write it abbreviated with just 3 letters, so it looks like sin, but it's really, we pronounce it sine. So sine of 30 degrees is opposite over hypotenuse, which is 1 over 2. And if we were doing cosine of 30 degrees, cosine is adjacent over hypotenuse. And so cosine of 30 degrees would be square root of 3 over 2. And the last one is the tangent function. And the tangent function, abbreviated with 3 letters, looks like tan. And that is the opposite over adjacent. And so sine of tangent of 30 degrees would be 1 over the square root of 3. So if you did trigonometry, these showed up a lot. You probably even put sine with this one, cosine with that one, and tangent here. And you may have even read this down to form that famous expression, SOHCAHTOA. Again, if you didn't do anything with this, that's okay. We're not going to cover it in this class, but it does lead me to the dad joke of the day. And that's because the tangent function, so the tangent of 30 degrees can also be thought of as the sine divided by the cosine. And you can see that when you plug them in, you get 1/2 over root 3 over 2. And we know how to invert and multiply with fractions. So this becomes 1 over 2 times 2 over root 3, which becomes 1 over root 3, and that does match with what we had before. So the tangent of 30 degrees is sine over cosine of 30 degrees. And so dad joke of the day, what is sine gerene divided by cosine gerene? What is sine gerene divided by cosine gerene? Well, if you notice, sine over cosine is tangent. So it is tan gerene. And there it is. Isn't that a cutie? Tangerine cutie. Okay, I'm done. That was enough. I get it. I get it. I get it. I'm done. Moving on. So what do we have? Those ratios are very, very helpful. I would encourage you to put those down. Up next is the converse of the Pythagorean theorem. Converse of the Pythagorean theorem says, go the other direction. If I have a triangle that has sides of A, B, and long side C, and A squared plus B squared equals C squared, then the triangle is a right triangle. So the converse, okay, I have now lost. No, the pages have disappeared. Please return to me. Okay, we've managed to jump forward quite a bit. Let's go back and see where we were. I have no idea why it did that. Okay, 47. Okay, here we were. Converse of the Pythagorean theorem. The Pythagorean theorem says this. If you can make sides of, let's say, 3, 4, and 5, because 3 squared plus 4 squared does equal 5 squared, you have just created a right triangle. So the converse says, if you have a triangle with A, B, and C, and A squared plus B squared equals C squared, then ABC is a right triangle, and the right angle is opposite side C. So one of the practices we do is we actually determine whether the following lengths can actually be sides of a right triangle. What you do is you just check small side squared plus middle side squared. If they add up to the long side squared, the answer is yes. So for example, 3 squared, that's 9, right? So 3 squared is 9. 4 squared is 16. So 9 plus 16 is 25. But 7 squared is 49. So I would say no. As a matter of fact, this can't even form a triangle because 3 plus 4 has to be greater than 7, and it's not. So this is really bad. This is like really bad. All right. Let's see here. I think we have a school book page. So this is understanding the converse of the Pythagorean theorem. And so you start with yeah. Yeah, I don't know. That's sketchy to me. I wouldn't buy into that one. In any case, let's see here. How can we use this? What is the Pythagorean theorem good for? So if you are given points, like between points A and B, any points in coordinate space, you can use the Pythagorean theorem to find the distance between them. And they get into some pretty dense stuff here with like absolute values and everything like that. But I want you to take a look at this. I'm going to hide some of their stuff because I think it's overkill a bit. It's not incorrect. It is not incorrect. So don't get me wrong there. But I want your thought process to look like this. Here is one of my points. Okay. Okay, it's right here. It's the point 25. Here's another one of the points. It's the point 68. Okay. I'm not even going to look at this point. I don't even know why it's there. What I want to do is I want to walk from point C. I want to walk over until I'm directly under point D. And in order to do that, I have to move from 2 to 6. So I'm going to walk 4 units over. Now I'm standing here. How far up do I have to hike? I have to go 5 to 8. That goes up 3. So I've created a right triangle with a side of 3 and a side of 4. The question here is what's missing? And so Pythagorean theorem comes in. 3 squared plus 4 squared equals 25, which is 5 squared. So that means the question mark is 5. So no, it's so similar to what we did with slope of a line. Remember how you would go over 4, then up 3, and your slope would be 3 over 4. All you're doing now is squaring those numbers, adding them together, and then take the square root, and that'll give you the distance. So it's very, very similar to what we did with slope. Again, what they're doing isn't wrong. It just seems long, and they're generalizing to this fantastic thing called the distance formula, which again, you probably had to memorize if you were in high school or maybe even before now. They're talking about this one being in the middle schools. But do you need to memorize it? Not really. Just think, how far do I have to move? How far do I have to move? Those create sides of a right triangle, and I can just use Pythagorean theorem. But There's nothing wrong with what they've written. Everything they've written down is correct. Just sometimes I feel like they go a little too far for what's useful. So they will give you points and you find the distances. So they have their distance approach in the book. I'm going to show you how would I do it if I use Scott's approach. Okay. Well, here we go. So I would take the point 7, 4. Okay, so over 7, up 4. And I have the point -2, 1. Okay, -2, 1. And I have the point 10, -5. Okay, 10, -5. Okay, so now all I'm doing is I'm just saying how far over do I have to walk? I have to walk from -2 to 7. That's 9. From 1 to 4, that's 3. Got it. 3 squared plus 9 squared. Well, that's 9 plus 81. That's 90. Okay, so this length right here is the square root of 90. That's it. I didn't have to memorize a formula. I don't have to memorize a formula. You don't have to memorize a formula, but you can. You always can. Let's go from this point. So let's see here. How far down do I have to go here? That's from 1 to -5. So that's going down 6. And then going across from -2 to +10 is 12. Got it. 6 squared plus 12 squared. That's 36 plus 144. That's 180. So this length right there is the square root of 180. And then lastly, I'll change color just so we can kind of see over here. So I want to go over. I need to go over 3 units because from 7 to 10. Now I need to go down from +4 to -5 is 9. That's 3 and 9. Well, I already did 3 and 9, and I know it's this. So this side right here becomes the square root of 90. So now I have a triangle that looks like this. Square root of 90, square root of 90, and square root of 180. And guess what? These two sides are the same, which means it is isosceles. And if I want to show that it's a right triangle, then take the small sides, square root of 90, square it. Square root of 90, square it. And I'm checking, is this the same as the square root of 180 squared? A squared plus B squared equals C squared? Well, square root of 90 squared is just 90. Square root of 90 squared is 90. Square root of 180 is 180. Yes. So this is actually a right triangle. Now, again, I didn't do that with memorizing any formulas. All I did is kind of walk a path, go over and up, count those. I think it's going to be much quicker to do that, me personally. All right, let's see here. How can we use the distance formula to develop the equation of a circle? Well, if you're trying to find the equation of a circle, we need to go over and we need to go up and we need to form that distance. So going over would be to go over from h to x. So this would be x minus h. And to go up from k to y would be y minus k, because that's just whatever that height is. You just subtract them. So if we're doing the Pythagorean theorem, because now we're doing the Pythagorean theorem, we have this plus that is equal to r squared. And guess what, folks? That right there is the equation of a circle. And all you do is plug in your h and your k, which is your center, and plug in your r value, which is your radius, and then xy is any point on the circle. So you can tell if a point is on the circle, or you can tell if you have a couple points if they form a circle. So there you go. I know they make it look a little bit more complicated, but that's it. Very, very cool stuff. Yeah, I think we'll do some stuff. Let me see here. Let me jump to GeoGebra real quick, just to show very briefly what is really cool about the Pythagorean theorem. So I'm going to build us a right triangle. Okay. And that means I need a perpendicular from here to there. And then I'll just pick any point out here on there. And that gives me a segment. Okay. So now I have a right triangle. And I can move these around. I can move this around, right? I can even shrink this back in so I can make whatever kind of right triangle I want. That's up to me. Now let's see. What I could do is come down here to regular polygon, and I can select two of these and say 4 vertices, and it makes me a square. And if I take two of these and say 4 vertices, it makes me another square. And two of these and 4 vertices, it makes me a third square. And why is this kind of cool? This is kind of cool because I can now take and say I can adjust these. So the right angle stays, but I can actually figure out what is the area of all of these pieces. And if I add the two areas, the two small areas together, guess what? It equals the large area. I know, but let's jump down and actually see it happen over here because maybe you don't trust me. So we've got poly 1, poly 2, and poly 3. So what I'm going to do, poly 2 turns out to be the big one. So I need poly 1. Poly 1 plus poly 2 is equal to C. Let's see here. No, it's not. Poly 2 equals that. Poly 3 equals that. Oh, I did poly 1 plus poly 2. I just told myself not to do that. Poly 1 plus poly 3 gives me this 30.9691, and that's exactly the same as the area listed here for poly number 3. So as I change those, what you'll notice is the area of poly 3 matches the poly 1 plus poly 2. That is really cool. And if you think about it, the length of the side here is being used for a square. So the area of the square would be a squared. The area of this one would be b squared. So a squared plus b squared has to give you c squared. It has to. Now, the reason why I think this is kind of cool is, well, let me delete all those polygons. And let me go back and try a different sized regular polygon. Let's see how you like this. I'm going to make pentagons. And this is what I think you'll find cool, or at least I hope you will. Okay, so there they are. That's kind of cool, right? See how they're all kind of sitting on the sides. Again, I could move these around and change those. And guess what's great about this? The area. And I did it this way, area poly 1, poly 2, poly 3. So I'm going to come down to my algebra over here. And I'm going to say poly 1 plus poly 3. And guess what? Poly 1 plus poly 3, this small one plus the middle-sized one, add them together, you get the area of the big one. Every time, no matter when you pull it, 639, 639. So it doesn't matter. It doesn't have to be just a square. As long as they are, all three of these shapes are similar, then the area of the small one plus the area of the middle one is always going to equal the area of the big one. And that is pretty cool. All right. Well, I hope you enjoyed that. That's it for this section. Enjoy. If you have other questions, please let me know, and I'll see you in class. Off you go.